Alright, in this video we're going to continue talking about properties of functions. There's quite a lot to get to, so we're going to try to go through it as quick as possible. First thing we're going to talk about is continuity. A graph, or a function rather, is going to be considered continuous if its graph has no breaks. So if there's no breaks in the graph, we're going to say it's continuous. When we get to calculus, we're going to get a better definition. But we need the idea of a limit in order to actually define continuity. So for our purposes, we're going to say the graph has no breaks. A graph will have discontinuity when you, and we'll just say, have a break in the graph, right? So if you have a break, you're discontinuous. If you don't have a break, you are continuous. There's three types of discontinuities. And each of them are in these pictures here. You'll notice this one's continuous. I can draw the entire graph without having to pick up my pencil. This one is a removable discontinuity. So it goes like this, and then we have a little spot there. So if I'm drawing the graph, I'd have to pick my pen up here, put it down, do this, and then draw a little dot there. You'll notice that these two graphs here, the second and the third, look very, very similar. The only difference is this actually has a function value defined. This has a y value at this x value a, and this one doesn't. It doesn't matter if you have a y value or not. As long as there's that little spot right there, it's a removable discontinuity. Now, it's called a removable discontinuity because you can remove the discontinuity by simply placing 1 point on the graph, right? If I put 1 point on the graph, I now have a continuous function. There's a jump discontinuity, and that should be pretty obvious based on the picture. It stops here, it's jumping up to here before it stops or starts again. So jump discontinuity, and then infinite discontinuity. So that's going to be here at A as well. This is called an infinite discontinuity because it would take infinitely many points to connect these two things, as opposed to this was just one. So those are the types of discontinuities. Let's talk about when they happen. A removable discontinuity happens when you can divide out a factor from the denominator. So we'll say you can divide a factor from the denominator. And that factor is going to create that removable discontinuity. They're also called holes. And pretty much that should be pretty straightforward based on the graph. Jump discontinuities mostly happen with piecewise functions. There's going to be other times that deal with absolute values, and really an absolute value is a piecewise function. And then infinite discontinuities is when you cannot divide out a factor. So you cannot divide a factor out from the denominator. And those are going to be called vertical asymptotes, and you've probably seen vertical asymptotes before. So let's try to find some points of discontinuity. Find any points of discontinuity in the following, and then classify each point. So if we're starting with x squared minus 9 over x squared plus 5x plus 6, the first thing I want to do is factor the numerator and the denominator. So we have a difference of squares in the top, so x plus 3, x minus 3. In the bottom, we're going to get x plus 3, x plus 2. So if we think about what's going to divide out and what doesn't, we can divide out an x plus 3, and then this x plus 2 can't divide out. So this x plus 3 is going to give me a hole, and this is going to give me a vertical asymptote. So I'm just going to abbreviate VA. Where these things are going to happen is where these turn into 0. So we're going to say hole when x equals -3, and a vertical asymptote when x equals -2, right? If we set that equal to 0, solve, we're going to get -3 and -2. In order to kind of see what's going on with this one, we kind of have to think about what the graph would look like. If I take an x value, let's say x equals 0. The numerator is 1, the denominator 1, so my y value is going to be 1. If I take x equals 2, the numerator is 3, the denominator is 3, so 3 divided by 3, my y value is going to be not 3, but 1. You can kind of see that it's going to be 1 everywhere, except if we go to the left of negative 1. So if I pick, say, negative 2, the numerator is negative 1, the denominator is negative 1, but you take its absolute value. So we're going to get actually negative 1. Now if we put negative 1 in here, we're going to divide by 0, and that can't happen. We can't just divide this out because its absolute value, it's not a set of parentheses. So this is its own little function. We can't really divide that out. So if we were to look at the graph, everything to the right of negative 1 has a y value of 1. Everything to the left has a y value of negative 1. And there's no value at 0 or at negative 1. So looking at the graph, this is going to be a jump discontinuity. And that's going to happen at x equals negative 1. Same thing we can kind of think about here with c, is if we just kind of graph it, see what happens. I have the value or the function x plus 1 when I'm greater than 0. So I'm not equal to 0, I'm just greater than 0, so I'm going to leave an open circle there. So my graph kind of looks like that. X minus 1 everywhere less than 0 or equal to 0. So we get a closed circle there. Graph looks like that. You can see that we have a jump at x equals 0. So that's finding our discontinuities. Next thing we want to talk about is increasing and decreasing, and this is going to be based on the rate of change. Remember that the rate of change is the slope. So function is going to be increasing on an interval if the rate of change is greater than 0 or positive. Decreasing on an interval if the rate of change is less than 0 or negative. So for our purposes, we can't really think about the slope unless we can see it. In calculus, we're going to have something called the derivative, and that's going to tell us the slope or the rate of change. But until we can do that, we actually have to look at a graph. So looking at the graph of x squared over x squared minus 1, we have it right here. I did not put that on your notes, so you might want to draw the picture. This is going from negative 5 to 5. But if you look at it, we can kind of see that over here my slope's positive. It's not super positive, but it's positive, and then it keeps going positive. And we pick back up here, positive, 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 positive. Then my slope right there is 0, right? It's completely flat. Then if we follow it, we start getting negative slope, negative slope, negative slope, negative, 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 negative. So if we're thinking about the intervals on increasing and decreasing, we're increasing on the interval negative infinity to 0, and we're decreasing on the interval 0 to infinity. Now notice that 0 gets parentheses on each one because we're not really increasing at 0. Our slope was 0, right? We're transitioning from an increasing to a decreasing, so it's not increasing or decreasing there. It's when we change. Just like 0 is technically not a negative number. It's the transition between positive and negative. So justify your reasoning. Increasing here because the rate of change is greater than 0. And we're decreasing here because the rate of change is less than 0. Alright, last thing we need to talk about are extrema. And the extrema of the function are the greatest and least y values. Or you could say dependent variable, output, any of those things, but it's the greatest and least y values. Now there's different types. There's going to be local extrema and absolute extrema. This could also be called relative or global depending on the book that you're looking at. So a local extrema is the greatest and or least, right? It's either going to be the greatest or least y values on an interval. And then global or absolute are going to be overall. So we're going to say over the whole function. Now, note that all absolute extrema are also relative extrema. Now, there's going to be two types of extrema, maximums and minimums. Maximums, these are the points that are greater than every other point. And this happens when the function changes from increasing to decreasing. And this idea is going to be really, really, really important in calculus. Knowing when we're changing from an increasing to a decreasing function gives us a maximum. Likewise, the minimum are going to be the least values. They're going to be, I guess the way this is written, we should say are less than every other point. And this happens when you go from decreasing to increasing. Right, so if you think about increasing means a positive slope, decreasing means a negative slope, well, that point right there is higher than everything else, so it's a maximum. Decreasing to increasing is going to give us a minimum. If we think about a function that looks like this, we're going to have relative maximums here and here, because on this little interval, this is the highest point. There are higher points other places, but on this little interval, that's the highest. We have a local or a relative minimum here. This relative maximum is also going to be an absolute maximum. The graph doesn't go any higher than this. This is not going to be the absolute minimum because this function goes down forever. So let's look at an example and call it quits on the video. So find all extrema of that function x to the fourth minus 7x squared plus 6x. Justify each solution. So in the interest of time, we're really only going to find one. So we're going to pull our graph up. So x to the fourth minus 7x squared plus 6x. I'm going to hit zoom 6 to reset my window to the standard viewing window. So it's going to go from negative 10 to 10. And you'll notice that my graph isn't quite good enough, right? It doesn't quite go down far enough. So I'm going to change the window so my y value is shorter. I also don't need all this other stuff here on the x value, so I'm going to make that a little bit smaller as well. So let's go from, let's go negative 5 to 5 for my x, and then let's go, say, negative 15 to, we'll say, 5, and see if that gives us a better graph. Still didn't go down far enough, so let's change it a little bit more. Go to negative 25. And there we go. We can see the absolute minimum here. So let's find one of these together, and then the rest will be up to you. So again, everything we need to know is going to be under second calc. This time we're going to try to find, let's find a minimum. So we'll hit 3. Left and right bound mean the same thing. So if we go left of the minimum we're trying to find, so my little blinking thing is there. Enter. Right bound means go to the right of what we're trying to find. Hit enter. Guess means get on top of that. Hit enter. Now you'll see that the function has its minimum at negative 2.051, but the y value, the minimum itself, is negative 24.057. So we would copy that into a point. So I don't remember what they were. I'm just going to hit x, y. It's whatever we just talked about. And then our justification is going to be the function changes from decreasing to increasing. So the other two are up to you. And I'm going to stop the video right here. We'll see you in the next one.